Some solved problems for Chapter 19, starting with a battery with some internal resistance, kind of drawing the whole setup right over here, where this is its EMF, internal resistance, and then the resistor that it's going to be connected to. We know that we can write the terminal voltage to be simply the EMF minus the current times the internal resistance. We need to figure out what this current is. Well, what we have here is we have two resistors that are connected in series, and so we could write the equivalent resistance to be big R plus little r, and now we can simply say that the current that's flowing in this circuit must be equal to the EMF divided by big R plus little r, and now we have everything that we need to know. We can say that the potential is going to be equal to the EMF minus the EMF divided by big R plus little r multiplied by r, and we know what all these guys are. So for part A, we would say this is going to be 6 minus 6 divided by 71 plus 0.9 multiplied by 0.9, and come out with about 5.92 volts. And for part B, you're just plugging the numbers in, so I'll let you do that. Resistors in series and parallel. So we have some light bulbs, got some resistance associated with them. Part A, what happens if they're connected in series? Remember that if things are connected in series, the equivalent resistance is simply the sum of all the resistances. In this case, we have 3 light bulbs that have a resistance of 45 ohms, and then we have 3 light bulbs that have a resistance of 65 ohms. So my equivalent resistance is going to be 330 ohms. If I go ahead and connect them in parallel, a little bit different. I say 1 over my equivalent resistance. It's going to be equal to 1 over R1 plus 1 over R2 plus 1 over R3, so on and so forth. So what this is going to kind of work out to be is 3 times 1 divided by 45 plus 3 times 1 divided by 65, which is going to come out to be about 0.111. We have to go ahead and invert this to get the resistance, so flip that guy over, and we're going to say the equivalent resistance is going to be 8.97 ohms. Some more circuit problems here. We've got a battery with internal resistance hooked up to 2 resistors. We know that current's going to flow, and it's going to flow in that direction. I'm calculating first the current in the circuit. These guys are all hooked up in series, and so I can say the equivalent resistance is going to be 2 ohms plus 9.5 ohms plus 14 ohms, so 25.5 ohms. And now the current is simply going to be equal to the EMF divided by the equivalent resistance, so 9 divided by 25.5, and that's going to work out to be equal to 0.3529 amps. And now I need to show that the sum of the voltages around the circuit is going to be equal to 0. What we kind of do here is we say I'm going to work my way around this circuit, starting with right here. So the first thing I'm going to do is I'm going to gain 9 volts worth of potential. Then I'm going to go across this resistor right there. So I'm going to take off 9.5 ohms. That's going to be the resistance, multiplied by the current, 0.35. Going to work my way down over here. Going to lose 14 ohms multiplied by 0.35, so my resistance multiplied by my current. Go ahead, work my way, hit the 2 ohm resistor, so 2 ohms multiplied by the current, 0.35. And if you actually use this number instead of 0.35, this will indeed equal 0. Okay, here I'm going to solve a Kirchhoff's loops problem. First thing, I changed the problem a little bit. I just want to solve for I1, I2, and I3. So I've got 3 currents running through here, and I have 3 unknowns. Keep in mind that, take a look at I2 flowing right here. It's going to be I2 going across this resistor and I2 going across that resistor. These guys are in parallel, or in series, so they have the same resistance. So first thing I'm going to do is I'm going to use the junction rules. Take a look at this junction right here. Here I've got I1 coming in. Here I've got I2 coming in. I have I3 leaving, so I'm going to say I1 plus I2 is going to be equal to I3. That gives me one equation to use. Now I'm going to do my loop, and let's just kind of start at point A here. I'm going to do this loop, and what I'm going to say is, the sum of the voltages must be equal to 0 as I work my way along this loop. So I start at point A, work my way through the loop. I hit this 34 ohm resistor. I'm going with the current, and so that says I'm going to subtract. If I was going against the current, I would be adding. How much? It's going to be 34 ohms multiplied by I1. So I work my way here, past point H, come on in here. Now I go across this battery source. I'm going from the short side to the large side, so I'm going to add 45 volts. Now I'm going to be crossing the 1 ohm resistor. I'm going with the current. Now the current's I3, so it's going to be I3 multiplied by 1. Then I'm going to work my way past this one, still going in the direction of the current. So I'm going to subtract 47 ohms multiplied by I3. And now I have my second equation. For my third loop, I can pick either this loop right here, or I can pick this big loop up there. Let's just pick that big loop in red. So I'm going to start off here at point A. I'm going to go up here. I'm going to cross the 34 ohm resistor going with the current, so minus 34 multiplied by I1. I'm going to continue my journey, come across this guy right here. Now I'm going against current 2, so I'm going to now add 18 multiplied by I2. Continue my journey, still going against the current, so I'm going to add 1 multiplied by I2. I'm going to go across this battery, and I'm going to go across it from the large side to the small side, so I'm going to subtract this guy off, so minus 85, and all of this stuff is going to be equal to 0. Same with this one up here. Now I have my three equations. The physics is done. Now it's all algebra. So let's just say I'm going to start with equation number 3, and I'm going to solve this guy for I2. So I'm going to add those guys together, get 19I2. Just kind of isolate I2. So I2 is going to be equal to 85 plus 34 multiplied by I1 divided by 19. And let's just go ahead and calculate that out. So that's going to be 4.474 plus 1.789 I1. Now I'm going to go ahead and take equation number 2, and I'm going to solve this guy for I3. So I'm going to add those two together, subtract them apart, and set it equal to, and figure out what it is relative to I1. So at the end of the day, I'm going to say I3 is going to be equal to 45 minus 34 I1, divide that guy by 48. So I'm going to have 0.938 minus 0.708 I1. And lastly, let's go up to the rule that I got from the Junction Rule, where I've got I1 plus I2 is equal to I3. Now what I'm going to do is I'm going to take this expression for I2, stuff it in right there, take this expression for I3, stuff it in right there. So I1 plus 4.474 plus 1.789 I1, so that's my expression for I2. And this is going to be 0.938 minus 0.708 I1, so that's my expression for I3. And now I have something that's in the language of just I1, 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 and I1. So I can go ahead and say I1 is going to be equal to negative 1.0, about negative 1 amps. All the negative sign really does is it says, hey, this stated direction for I1, it was wrong. That's okay. Now we can go ahead and take this expression for I1, plug it in right there, plug it in right there, and get I2 and I3. What you're going to say is I2 is going to be equal to about 2.7 amps, and I3 is going to be equal to 1.7 amps. And the problem with capacitors, I got 6 capacitors, they're all the same capacitance. connect them in parallel. You connect capacitors in parallel, you simply add their capacitance. So this is going to be capacitor 1 plus 2 plus 3 plus 4 plus 5 plus 6. Since they all have the same capacitance, you can just simply say 6 times 4.8 times 10 to the negative 6 farads. Go ahead and you multiply that guy out, and you're going to get 2.88 times 10 to the negative 5th farad. That's the equivalent capacitance. Capacitors in series do the same. It's going to look like this. It's going to be 1 over C1 plus 1 over C2 plus 1 over C3 and so on and so forth. So that's going to, in this case, end up to be 6 divided by 4.8 times 10 to the negative 6. And that's going to be 1.25 times 10 to the 6 inverse farads if you want. Got to go ahead and invert this guy. So when you go ahead and do that, you're going to find CQ is equal to 8 times 10 to the negative 7th farads. And lastly, some energy storage with capacitors. Suppose I've got a circuit, kind of drew it over here, with just one single 250 picofarad capacitor hooked across a battery. If we want to store 4 times as much energy by adding a capacitor, how can we do that? Well, we could add a capacitor right here, or we could add a capacitor right over there. So what I essentially want to have is my potential energy final is going to be 4 times my initial potential energy, where potential energy is going to be 1/2 capacitance times voltage squared. So 4 times 1/2, got my initial capacitance and my initial voltage. Now here's the deal, I know what that is. I don't know what that is. This is what I want, and I don't know what that is. So pretty much the only way that I can solve this is if I can cancel these two voltages out. If I can force V2 to be equal to V1, then I can just go ship, zip, and I'm good to go. Oh, might as well cancel out my 1/2 while I'm at it. Now, how do I get that? Well, that means I must hook the capacitor up in parallel. So this is the one that I want to do, because I'm going to have the same voltage here that I'm going to have right there. So I won't be changing the voltage. Now that simply says that this new capacitance is just going to be 4 times the initial capacitance, so it's going to be 1000 picofarads. However, that's not the answer. That's going to be the equivalent capacitance of those two capacitors in parallel. So what that says is I want to take a 750 picofarad capacitor and hook it up in parallel, such that now the capacitances are going to add together to be 1000 picofarads.